Spectroscopy is the study of the interaction of light with matter. There are many forms of spectroscopy, largely defined by the energy of light that is used. Light can vary from very low energy, radio waves, to very high energy, gamma radiation. Light is categorized by the wavelength or the frequency of the light. Wavelength and frequency vary inversely, which means that light with longer wavelength has lower frequency, and shorter wavelength has higher frequency. The higher the frequency of the light, the higher the energy. Light can interact with molecules in many different ways. Light can make the nucleus resonate, can make molecules rotate, can make molecules vibrate, can make electrons change energy within matter, can eject an electron from matter completely, and can diffract around nuclei. Most of these interactions are quantitative, which means that light can be used to determine what matter is present and also how much of that kind of matter is present. In this video, we will be examining the interaction of infrared light with molecules. Infrared light is lower in frequency and therefore energy than visible light. Infrared light is a major component of radiative heat. Night vision goggles most often take infrared light as the input and then outputs visible light in the same patterns and intensities, allowing warm bodies to be seen even in the absence of visible light. In infrared spectroscopy, infrared light is passed through or reflected off of the matter of interest. The infrared light interacts with the natural molecular vibrations that are always happening. Light, also known as electromagnetic radiation, has a magnetic aspect. Many molecules also have magnet-like properties called dipoles. When the magnetic aspect of the light and the vibrating dipoles within the molecule interact with constructive interference, energy is transferred from the light to the molecular vibrations, and the light is absorbed. Constructive interference is found in many other places. In music, when notes of a major chord are played together, the constructive interference produces new sound. Dissonant sounds can be the result of destructive interference of sound waves. When the wind matches the resonant frequency of an antenna, the reinforcing wind waves will cause the antenna to vibrate. When the frequency of vibration of the infrared light matches the vibration of the molecule will vibrate with greater displacement, absorbing the energy of the light. This absorption can be plotted versus frequency of light, and a molecular signature can be found that can be read to determine the type of bonds within the molecule. There are two major types of vibrations within molecules. The higher energy vibrations are mostly bond-stretching vibrations. For example, when a hydrogen atom and an oxygen atom are bonded together, the bond is very strong and has a large dipole. When this bond vibrates, a very large peak is recorded on the high end of the IR spectrum. The bond between carbon and hydrogen is also strong, but the dipole is smaller. When a CH bond vibrates, a smaller peak is created, but with similar energy. The frequency of the vibration also depends on the mass of the atoms. A bond between a carbon atom and a bromine atom resonates with much lower frequency light because the bromine atom is very heavy. The other type of vibration is known as a bending vibration. Instead of a bond between two atoms only, bending vibrations result in the distortion of a larger portion of the molecule with many atoms and bonds involved. These vibrations are mostly at lower energy than bond vibrations. We hope you've enjoyed this video, a collaborative work between the Missouri Western State University School of Fine Arts Digital Animation Program and the Missouri Western State University Department of Chemistry. We would appreciate a like on this video and for you to follow the MWSU Chemistry Department YouTube channel for more videos like this and for chemistry demonstrations.